Hello everyone. In today's lecture, we will continue our discussion on memory hierarchy. More specifically, we will be talking about virtual memory today. As you may remember from our previous class, caching is a way to provide past accesses from CPU to the main memory. The virtual memory, on the other hand, completes the other half. In other words, the vast memory capacity requirement of the ideal memory system. So let us be more specific and talk about the details explaining what we mean by that. So far, we have discussed the speed issue and caching to close the gap between blazing fast CPU speeds and lagging slow memory access times. This was a CPU transparent operation to give an illustration of a fast and a moderately sized memory system. Another dimension to the ideal memory system is the large capacity. In other words, giving the illusion of unlimited capacity being accessible to the CPU. Virtual memory idea expands the address space to what's possible with the given architecture. So conventionally, its address space is larger than the practical address space. There are also other advantages of virtual memory concept, such as providing each running process a uniform address space. We'll give more details about that later. And it protects address space of each process from corruption by other processes. The concept of virtual memory can also allow memory system and the data stored in it protected by various other processes running in the system. Such data might be very sensitive and valuable for maintenance of the overall operation. In order to understand virtual memory concepts, we need to look at a few basic stuff, such as virtual and physical address spaces. An address space is an ordered set of non-negative integers from 0 to some predetermined number. For example, if an address space of n is used, we say the non-negative integers start from 0 and ends in n-1. Assuming that n is a power of 2 raised to the some power lowercase n, modern CPUs are in that context are either 32-bit or 64-bit machines, providing 2 to the 32 or 2 to the 64-bit address spaces. If the consecutive numbers are used, the address space is called linear address space. This address space is virtual, in other words, because there might be no physical resource to address that many bytes. So there is another integer we usually come up with, which is m, which equals 2 raised to the power lowercase m, to substantiate the amount of address lines for the physically available memory. As you might guess, if m is less than n, then each byte in physical memory can have more than one virtual address. This is what people choose in practice, but in the past, particularly in few DEC systems, m greater than n is also chosen for different reasons. So far, in our ISA and microarchitecture discussions, we have always assumed physical addressing. This is because physical addressing is a straightforward concept and is easier to understand. Early PCs used physical addressing, for example, and systems such as digital signal processors, embedded microcontrollers continue to do so for a few obvious reasons. However, most of the modern PCs use virtual addressing, as shown to the right of the figure. We use load instruction in this example to show how physical and virtual addressing is implemented in computers. In our example, load, LD instruction, loads 4 bytes from main memory. In the virtual addressing case, CPU generates the virtual address first, and then this gets translated by the so-called Memory Management Unit, or MMU, to physical address before being sent to the main memory. The address translation is handled by both CPU chip and the operating system kernel. Virtual and physical memories are partitioned into fixed-size blocks called virtual and physical pages. We abbreviate them as VP and PP in this slide. And they are of size P to the P bytes. In a way, virtual memory becomes the secondary storage, such as disk or SSD or some other secondary storage which is slower compared to main memory access times. And main memory becomes our new cache in this context. And whatever address using virtual address line, the corresponding physical address is found and searched in the main memory. Therefore, it could happen to be in the main memory whose state is shown as cached, or it could happen not to be present, in which case we use uncached state labeling. There might be also holes in the virtual address space as well. These holes provide flexibility for programs which dynamically allocate memory. The label for this is called unallocated. Another point here we need to make is the large cost associated with page misses, in other words, serving a missed page in memory is from the disk, which amounts to hundreds of thousands times slower compared to a typical DRAM. So to alleviate this burden, page size is kept large, and to minimize the misses, DRAMs are structured as fully associative. As with any cache system, virtual memory system must have some way to determine if a virtual page is cached somewhere in DRAM. And if so, the system must determine which physical page it is cached in, etc. If there is a miss, the system also must determine where the virtual page is stored on disk and bring it on the DRAM. Page table is a data structure that maps the virtual pages to physical pages. The address translation hardware reads the page table each time it converts to a virtual address to a physical address. The operating system is, on the other hand, responsible for maintaining the contents of the page table and updates also, and also the pages that are transferred back and forth between the DRAM and the disk. On the right, there is an example with 8 virtual pages, and only 4 of them are cached in DRAM. 2 of them are not cached, and they are located on disk, and 2 other virtual pages are not yet allocated. One of the observations is that the DRAM cache is fully associative. In other words, any physical page can contain any virtual page. The top of the page table is pointed by a control register in CPU named Page Table Base Register, or PTBR. This register holds the main memory address where the page table is stored. As can be seen, n-bit virtual address has 2 components, a p-bit virtual page offset VPO and n-p-bit virtual page number VPN. And MMU uses VPN to select the appropriate PTE, which means the table entry, the page table entry. For example, VPN 0 could be selecting PTE 0, and similarly VPN 1 could be selecting PTE 1, etc., etc. Finally, the physical address is given by the concatenation of the physical page number PPN obtained from the PTE and the VPO from the virtual address. In this case, VPO and PPO are the same thing. So let us go over the steps required to complete the requested data transfer to the CPU in case of cached or uncached data in the main memory. These cases are known as page hits and faults. In the case of a page hit, the processor generates a virtual address and sends it to the MMU. In the second step, the MMU generates the PTE address and requests it from the cache and main memory in this case. Step 3, the cache main memory returns the PTE to the MMU. In the step 3, the MMU constructs, in step 4, the MMU constructs the physical address and sends it to the cache, or the main memory. In the final step, the cache main memory returns the requested data word to the processor. In the case of page fault, the first 3 steps shall be the same. In other words, the PTE will be returned to the MMU for data request. However, the valid bit in the PTE is 0. So the MMU triggers an exception, which transfers control in the CPU to a page fault exception handler in the operating system kernel. The fault handler identifies a victim page in physical memory, and if that page has been modified, it pages out to the disk. The fault handler pages in the new page and updates the PTE in memory. The fault handler returns to the original process, causing the faulting instruction to be restarted. The CPU resends the offending virtual address to the MMU. Because the virtual page is now cached in physical memory, there is a hit, so we return to our first case, page hit case. The activity of transferring pages between disk and memory is called swapping or paging. The strategy for waiting until a miss occurs is known as demand paging, and is widely used in all of the modern computer systems. So far, we have seen single page table for mapping virtual address space to the physical address space. In fact, operating systems provide a separate page table and therefore separate virtual address space for each process. The combination of demand paging and separate virtual address space pose a significant impact, have a huge impact in the way the memory is managed in a system. For example, each virtual address space is uniformly divided between stack, heap, code, and data fields, where heap and stack fields can dynamically grow. Such a uniformity simplifies the design and implementation of linkers and loaders. Yet another example could be these fields being private to each process, and yet in some instances some of the kernel code is shared, or standard C libraries might be shared. So the operating system can arrange for multiple processes to share a single copy of the code by mapping appropriate virtual pages in different processes to the same physical pages as shown in the figure on the right. Finally, as mentioned before, it allows, this whole virtual memory concept allows easier memory allocation, as the heap and stack fields can dynamically change without knowing where the pages are stored in physical memory. If page table is only stored in the main memory, the MMU will have a lot of memory accesses, and each of these memory accesses will have about tens of clock cycles. The total time might be huge enough to eliminate all the advantages offered by the virtual memory. So people looked at different strategies to solve this problem. It is found that one can reduce memory accesses through using internal, in-chip caches. Translation Leukocyte buffer, or TLB, in short, is a caching technique inside the MMU that translates the virtual address to physical address. It holds the recently addressed pages to speed the access. There are also other hardware supports in modern architecture, such as segmentation and for protection mechanisms to permit appropriate isolation and sharing of programs and data, which are a bit beyond the scope of this class. So I'll basically recommend you guys have supplementary documents and also other textbooks to read more about these subjects. In this class, we covered basics of virtual memory systems in computers. We talked about various concepts such as page tables, page hits and faults, and the interaction of the hardware and the operating systems in managing the virtual addressing. We also gave brief set of advantages of virtual memory in current modern computer systems. Please feel free to drop any questions you might have about today's lecture into my email box, and I'll be more than happy to help you with your questions. Thanks a lot.